Assalamualaikum warahmatullahi wabarakatuh. We are from Group D and I am Fitrah Humaira with my two other friends, Galeya and also Nurfatihah. We're going to present about our project, the Autonomous Visual Recognition in Smart Farming. Firstly, for the problem statement, we have identified three major problems for this project. So the first problem is the agriculture productivity. Farmers prioritize agriculture productivity to meet the rapid growth of food demands over the years, and the implementation of artificial intelligence, or known as AI, and machine learning in farming practices help the process to become more data-driven and accurate. The second problem is the harvesting time. Crops or the product need to be harvested at the right time to ensure that the harvested fruit has the best quality. Harvesting crops too early or too late can result in unripe and overripe fruit. And the last problem is on the labor shortage. The farms are always facing the problem of finding workers. Therefore, many of them have started to implement technologies in the system, especially during the harvest season. For dataset, in this project, we create a customized dataset to fulfill the requirements needed for the fruit condition detection. We also manually gathered my image from publicly available datasets such as Kaggle and also publicly available images from Google Image Search. Our dataset consists of images of five common fruits, which are apples, jackfruits, mangoes, oranges, and also strawberries. So each fruits have 20 images of bad fruit and 20 images of good fruit. So the image provided is the structure of our dataset that we store in a folder called Fruit Detection Dataset. According to fruit detection and recognition based on deep learning for automatic harvesting, an overview and review by CSCI4340 2023, they stated that YOLO is an algorithm that can be categorized as a classic and advanced fruit detection algorithm. YOLO has emerged as an important part in a wide range of applications across several fields. YOLO stands out among other image detection algorithms due to its outstanding balance between accuracy and speed. Next, moving on to the YOLO V8 literature review. According to a comprehensive review of YOLO architecture in computer vision, from YOLO V1 to YOLO V8 and YOLO VNES, by Tervan and Cordova Esparza, 2024, they stated that YOLO V8 is a powerful and flexible version of YOLO with object detection, segmentation, and tracking capabilities. YOLO V8 used C2F backbone and anchor-free head for a better precision. Lastly, for the literature review of YOLO V11, according to YOLO V11, an overview of the key architecture enhancement by Khanam and Hussein 2024, they stated that YOLO V11 enhanced the YOLO V8 architecture with faster C3K2 blocks for the backbone and spatial attention C2 PSA that improved accuracy and on small and complex objects. For the methodology, we have seven key steps, which include dataset collection, dataset preparation, dataset preprocessing, data annotation, fruit condition detection model, performance evaluation, and also testing fruit condition detection model. So the first step is dataset collection, which we already discussed in the dataset part. So we're moving on to the dataset preparation. So all the fruits are labeled according to their condition and type in order from 1 to 20. For example, like bad apple, we label it as BAPP1, and good apple, we label it as GAPP20. Also with the other fruits. So besides that, the image are also placed in the folder according to their conditions and type. The third step is the dataset preprocessing. For data preprocessing, we perform steps to understand the dataset structure and image distribution. We perform EDA, display sample image, analyze the image size, detect corrupted image and also resize the image. For the first step, which is data annotation, fruit images are labeled with bounding boxes and class labels by RoboFlow as the tools. Next, for the fruit condition detection model, the models are created for three algorithms, which is YOLO V8N, YOLO V8S, and YOLO V11N algorithm. The models are trained by feeding them with the image dataset to ensure the model learn from the labels. And we also perform hyperparameter tuning. The sixth step is the performance evaluation. The trained model is evaluated using MAP, which is the mean average precision, and also the precision and recall. So the last step is on the testing fruit condition detection model. All models are tested via predictions using the validation set.
Assalamualaikum warahmatullahi wabarakatuh. My name is Galeya Binti Herman Gallego and my mention number is 2216574. So I will be moving on to the experimental setup as well as the code demonstration. So firstly is the data analysis. So for our data description, our data set is actually a customized data set which consists of images of 5 different fruits, which are apples, jackfruits, mangoes, oranges, and strawberries. So basically we collected these images through sources such as Google Images and also Kaggle. So all of these fruits were then divided into different folders based on whether they are good or bad according to each fruit. And each class consists of 20 images. Moving on now, I will be continuing with our data analysis section where I will explain the EDA code. So it is important for us to do EDA to understand our data and to find any corrupted images as well as to see the distribution of the data set that we have. So firstly, what we did was we wanted to see the distribution of class in our data set. So this is the code that will produce a histogram that shows the number of images in each class. So first and foremost, um, it counts images inside a folder where I pointed to the dataset folder, which is called images. It will count into each folder, which is the different classes, how many images there are in each folder. And then here is the code for the plot. And then the output, as we can see, is a histogram that shows that each class has the same number of images, which is 20 images per class. Moving on, we also did a code that printed out sample images that are inside the dataset. So this is important because it shows us that every image has different dimensions and different sizes. So then we can prepare for pre-processing where we can resize these images. And last but not least, we did a code that shows us the difference and the distribution of the width and height of the different images. So the output is a histogram that shows the differences in width and height. So then we can adjust later on to optimize our model. Next is data preprocessing. So firstly, we wanted to identify the number of corrupted images in our dataset. So this is the function to find any corrupted images, which are maybe missing images or null images. So after we ran this code, we get that there are 0 corrupted images. After that, we wanted to resize each image into this dimension, which is 256 times by 256. So we decided this because it is not too big and it is not too small for us to train the dataset. And then after resizing it, it will be saved back into each folder according to the class. So this is the output. It will show that for an example, all of the Appleback classes are resized and saved into the new folder called image resized. After that, we did data annotation. As we know, the YOLO model will need labels of annotated labels based on bounding boxes. So we used RoboFlow as well as its tools to annotate each image that we have according to its class. So after annotation, we split the data. So basically the data set was split into training and validation subsets to efficiently assess the model performance. So we used RoboFlow's data set built-in dataset management features where the dataset was divided into 80% training set and 20% validation set. So after using the management features, it prompted or it produced a folder of trained images and valid images where it contained images as well as labels from the annotated images that we did before. So moving on to the code demonstration in which I will explain how we trained our three YOLO models and how we get the results. So first and foremost, we imported YOLO from the Ultralytics library that we have installed earlier. And then basically we call the YOLO model version that we want. So for example, for YOLO version 8S, it is called YOLO v8s.pt. For YOLO version 8N, it's called YOLO v8n.pt. And for YOLO version 11, it's called YOLO 11n.pt. So the three of these models were trained with the same parameter values and the same number of epochs, which is 30 epochs. So we trained these three models to our custom dataset, which is the images dataset that we generated from RoboFlow earlier. But since this is YOLO, so it requires us to have a YAML file in which this file basically points to the images dataset. So after running this code, it will basically generate the training logs as well as the results will be stored in a folder called runs detect. And for example, if it's YOLO V8S, it will be saved in a folder called YOLO V8S. So this is an example. So the folder contains the model training weights, confusion metrics, the graphs, and as well as the training batches. So basically we applied the same code, sorry. So basically we applied the same code to all three models to ensure that we have a fair comparison. After training, we used the val function to basically evaluate and find the evaluation metrics. So for the evaluation metrics, we basically find 5 different evaluation metrics, which is the MAP value for 0.5 to 0.95, the MAP for 0.5, the MAP for 0.75, the precision value, as well as the recall value. So next, I'll be explaining the hyperparameter tuning that we have applied to our three YOLO models. So we decided to do a random search hyperparameter tuning to all three models using the same techniques and the same parameter ranges. So it'll be much more fairer for comparison. So why we decided to choose random search? Because we think that it's simple, fast, and effective, especially when only a few hyperparameters can significantly impact the performance. So we didn't pick grid search because it tests all combinations exhaustively. So starting off with our code, basically we imported necessary libraries, which is YOLO, random, SVOS, and time. And then we set the parameter ranges, which is the initial learning rate, batch, weight decay, momentum, warm-up epochs, and patience. So these are the value ranges that we put. So later on, random search will take a random value within these ranges. After that, we specified the number of trials to run, and we set the initial best MAP to 0, and we prepared to save the results in a CSV file. So I chose 5 trials because it won't take too much time, because if the epoch is 30 epochs, then it will run for 5 times, which means that is a total of 150 epochs. And then this is just a code that checks if there is an existing CSV file. If there is, then it will delete that file. And then we enter the main loop. So basically this loop will run for 5 trials. In each trial, it will randomly sample a set of hyperparameters using random uniform and also random choice. And then it will print the selected values for tracking. After that, we will print the YOLO version 8 nano model and begin training using the train function, and it will pass in our dataset and the randomly chosen parameters, and the training will run for only 15 epochs with a smaller only 15 epochs using the parameters that the random search has chosen earlier. And after that, the results will be saved in a folder called runs YOLO V8 and random search. After training, it will immediately validate the model using the val function and extract key evaluation metrics such as the MAP values, precision, recall, and training duration. After that, we collected the results in a dictionary and append them to a result list. And each result is also written to a CSV file to keep track of all our trial outcomes. And if the current model achieves a higher MAP than the best so far, then we will update the best score and save the corresponding parameters. So after all the trials are complete, we print out the best hyperparameters found and the highest MEP achieved. And yeah, so as I said earlier, after the random search trials have finished, it will create a CSV file showing the different parameters as well as the different results that it got in this file here. Moving on, after training the model with hyperparameters, we will need to train the final model using the best parameters that we found. So this is the code for the final training with the best hyperparameters that we found earlier. So during this training, we will use a much higher epoch value. So I have set the epoch value to 50. And then we also print the evaluation matrix. And then we will get the results with the hyperparameter tuning. This was applied to all three YOLO models with the same hyperparameters. All right.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurfatihah Hamzah, metric number 2210378. Now, let's look at the results from our hyperparameter tuning using random search. We tested three models, YOLO version 8N, YOLO version 8S, and YOLO version 11N, across different combinations of learning rate, batch size, weight decay, momentum, warm-up epoch, and patience. After running the random search, we identify the best parameter sets for each model. So based on the table, hyperparameter tuning revealed that YOLO version 8N outperformed the other models by achieving the highest mean average precision at a threshold of zero point 0.5. This suggests that YOLO version 8N demonstrated stronger learning capabilities and generalization in detecting fruit conditions. Its superior performance makes it highly suitable for smart farming applications where accurate and reliable object detection is crucial. Next, we analyze the model performance comparison before and after hyperparameter tuning. So before tuning, YOLO version 8S showed the best baseline performance. It achieved the highest map at zero point 0.5 of 0.7371 and map at 0.50.95 of 0.5077, indicating strong initial detection accuracy. After applying hyperparameter tuning, we observed some shifts. YOLO version 11N showed notable improvement, particularly in precision, achieving 0.6769, which was the highest among all models. Its map at zero point 0.5 also reached 0.6594 with a balanced recall of 0.6777, demonstrating stable and consistent detection performance, while improvements in map at 0.5, 0.95 were moderate across all models. The tuning process generally resulted in more balanced precision recall trade-offs. This indicates that tuning helped the models become more stable when dealing with both correct detections and reducing false positive or false negative. Overall, although YOLO version 8S had a stronger start, YOLO version 11N demonstrated better robustness and consistency after tuning. This made YOLO version 11N highly suitable for reliable fruit condition detection in smart farming applications, especially where varying environmental conditions can affect model performance. Let's take a closer look at this side-by-side comparison. On the left, we have the result from YOLO version 8, and on the right, we see the predictions from YOLO version 11. YOLO version 8 does a decent job in labeling fruits. It identifies multiple good apple and good mango instances, but we notice some inconsistencies. For example, some images show overlapping or redundant labels like good apple, and some fruits are missed entirely or classified incorrectly. On the other hand, YOLO version 11 shows clear improvement. It provides more confident predictions with probability scores on the label, such as good apple 0.7 or bad jackfruit 0.8. YOLO version 11 also detects more fruits per image, and the bounding boxes are more accurate and tighter. Now let's move on to the discussion of our experimental results. Initially, we observed that YOLO version 8S performed the best at baseline, achieving the highest map at zero point 0.5 and map at 0.5 scores before tuning. This means it had a strong initial capability to detect the fruit conditions accurately. However, after performing hyperparameter tuning, YOLO version 11N demonstrated superior performance in terms of precision and stability. Specifically, YOLO version 11N achieved a precision score of 0.6769 and a balance recall of 0.6777. This indicates that the model consistently identify both healthy and defective fruits, even under different environmental conditions. The confusion matrix and performance curves supported this finding, showing that YOLO version 11N maintains stable detection performance across various challenges such as poor lighting, complex backgrounds, and different fruit orientations. It also showed fewer misclassifications and less sensitivity to threshold changes compared to YOLO version 8N and YOLO version 8S. In contrast, while YOLO version 8N and YOLO version 8S were capable of making accurate predictions under ideal conditions, their performance dropped when faced with more difficult scenarios where the differences between good and bad fruits were subtle. This was reflected in their lower recall and confidence stability after tuning. Overall, our findings highlight YOLO version 11N's robustness and adaptability, making it a strong candidate for real-time fruit condition detection in smart farming application, where consistent accuracy is crucial. In conclusion, this project successfully developed an autonomous visual recognition system for smart farming using deep learning based object detection models. We created a customized dataset of 5 common fruits found in Malaysia and trained 3 models: YOLO version 8N, YOLO version 8S, and YOLO version 11N. While YOLO version 8S initially performed better, after optimization, YOLO version 11N demonstrated superior precision, stability, and overall performance across the key evaluation metrics. Importantly, YOLO version 11N maintained high detection accuracy even in challenging conditions, which shows its strong potential for real-world deployment in agricultural environments. Looking forward, there are several ways to further improve this system. We can expand the dataset with more diverse images, incorporate real-time data collection using drones or smartphones, and deploy the model on edge computing devices like Raspberry Pi or Jetson Nano for on-field use. With continuous advancement in AI and computer vision technologies, smart farming systems like this can significantly improve productivity, reduce labor dependency, and contribute to more sustainable agriculture practices. That's all from our group. Thank you so much for watching.